everyone. Sorry, I will need a switch for my okay. So I'm Yang from Institute of Computing Technology, Chinese Academy of Science. I'm here to present my submission to championship branch predictor called LVCP, a load value correlated predictor for TAGE-SC-L. So first, I will introduce two examples of the motivations of a load value correlated predictors. The first one is a code snippet from glibc memset function. So this one is a dynamic sized loop. It is very hard to predict with only branch history, but it's very easy to predict once you know the iteration counts. So next one is a small examples. When a loop exit branch sees a load value 5 of distance 5 away, the branch should know it will exit now. The next one is a little bit more complicated, called value locality. The code snippet here is a batched binary search. So you have a lot of keys and you search them one by one in the sorted key arrays. This is very difficult to predict because there is little correlations between the branches of different key. But the keys itself has value localities. If you see a key 1 in the previous iteration, you can predict the following series of branch using this value. I noticed this type of branch may be optimized by the compiler through conditional moves, but the exit branch, which is the hard to predict branch 1, is nearly impossible to eliminate by compiler. So for this branch, for this type of branch, if you know the key, for example here, you have a critical load identified for key 441. Last time it appears, it results in a series of branch history, TT, NTT. Then you just predict taken, taken, not taken, taken, taken. This one is our measurement of how these patterns are in the provided traces. We see a significant amount, around 30% of the misprediction comes from single load dependent branches. So my work is mainly focused on this single load dependent branch. This one is, the matrix is measured on by using an unlimited sized correlation table trained on a 4-element tuple, which is a branch PC, a load PC, load value, and distance between load and branch. So if this 4-element tuple can predict right and TAGE-SC-L predict it wrong, I will count that as the opportunity. So these opportunities is significant. However, there is a problem. This matrix is measured at commit time. So at commit time, you know every load before the precede to this branch. In actual predictions, you do not know every load before you when you predict the branch. So these are causing a timeliness issue. According to our measurements, around like 5 to 10% of these opportunities is actually capturable at predict time. Next part is I'll just introduce my design of how to capture some of these opportunities. On the right side is the high-level architecture. The green part is the newly added components, and the rest is the same, roughly the same as the TAGE-SC-L in 2016. So there's a the load tracking queues that keeps the tracks of the distance between a branch and 16 of its preceding loads. If the load values are ready, the values are used to check the search the correlation table for a tag key. The correlation table is a tag set associative structure. if there is a search hit, and we use a simple hard branch table to identify these hard to predict branches and to filter some of the noises from easy predicted branch. If it is a hard to predict branch and the load correlation table has provided a prediction, then we will use the prediction from this side. Otherwise, the original TAGE-SC-L is used. For the load tracking part, you need to precisely track the distance between a branch and its 16 preceding loads. So here's a queue that will a load will enters the queue when the load is get out of the predictor. So then after 16 loads, they will exit, and we observed some of the branches depend on long latency, long distance load. So we add a distance load buffer when a load PC, when load instruction exits the queue, they will enter the buffer, and the buffer is indexed by the load PC. This will keep some of the loads inside this buffer even after long distance. So if the value is ready after some time, the load PC has finished execution, the value and the PC and the branch PC and this branch 3 elements tuple will be hashed into a single digest and used to search the correlation table. The table is highly banked from 1 to like 16 to match the queue to avoid using multi-port SRAM. That's it. The next one is a little tricks of our implementations. So we allocate the correlation table only on mispredicted hard branches, and we use a probabilistic decay and for the useful counter to keep useful branches, useful entries in the correlation table. So you know, for one branch you have, in this case, 16 loads that can be correlated with. You don't note the correlation after you have trained your entries in the correlation table. So avoiding noise is very important. At prediction, the youngest confidence hit from the queue is used for the direction, because well, I think the more young is the load be, the more accurate the prediction will be. Otherwise, the smallest index from the distance buffer will win. This is just a random choice. For implementabilities, so there's a question here. So we do not know if there is a branch at predict time. So since the instructions are not yet decoded, we added a small cache-like structure called load marking table that will use 1 bit for a 1 bit for 4 bytes to indicate there is a load. The next one is MPSC. So we also introduced some special features in SC. The bias part is the same. The global history is shared by Li. This is proposed by Andrea in his cookbook. The local history part, we tried to be realistic and use a 32 entries per branch local history and 16 entries per set, which is like 256 bytes region. Past history is roughly the same with Andrea, and Li is also re-engineered according to Andrea. Our experiment setup is we have the Unreal one is the Championship 5 winner, and it's scaled to our story budget. And the baseline one is we reduce the local history to be more realistic, and the Li outer history component is updated only at commit time. And the other two compare is our TAGE-SC-L with lower storage budget and adding our load value correlated predictor. So this is the final result of the proposed predictor, and you can see that load-related features are more useful than other features that in the statistical characters. So for a conclusion, our proposed predictor considered a good implementability, and it improved the branch MPKI by 0.07 compared to on a ISO storage comparison. I consider there is a much more future design space that can be explored. For example, more than one branch correlations, and the noise filtering mechanism I introduced is very rough. Maybe some better mechanism can be used in the future. Thank you.